Hello everyone, I'm Zhang, a researcher from Microsoft Research. I'm glad to share our work, Retiarii, a deep learning exploratory training framework. This is the joint work with my colleagues Zhenhua, Fan, Yuge, Zhou, Mao, and Lidong. In this video, Zhenhua and I will co-present this work. As we all know, deep neural networks have become prevalent. DNN models are being adopted in both cloud and edge. More and more scenarios and applications are powered by DNN techniques. So it is important to design a good DNN model for each given task. Designing a deep learning model is very different from traditional big data tasks. For big data task, for example word count, developers write a script. After the script is executed on targeted data, we get the result. The task is done. However, a deep learning task is not training a given model. Instead, its goal is to find a good model for a specific task. For example, designing a DNN model for detecting faces on an edge device. It has both accuracy and latency constraints. Designing a deep learning model is mainly an exploratory process. It usually starts with a hunch, for example from some well-known, good-performing neural architectures as a basis, to produce a concrete model, then training this model to check how it performs. Based on the training performance, the developer manually or automatically refines the model for getting better performance. After checking its training result, the developer modifies the model again and trains it. This process is repeated until the desired model is found. We call this process exploratory training. Let's look at some typical modifications to models during exploratory training. The graphs represent DNN models. When designing a model, developers do some of these modifications to find better models. First, developers may replace an operator with another one. For example, changing activation operation from ReLU to leaky ReLU or mesh, or try to add skip connections. Also, there could be some rule-based modifications, like replace some specific layers with another one, or inserting operators after specific layers. Another modification type is generalizing a block structure. Inception block is shown on the left. It has 4 passes, with one operator on each pass. It's intuitive to try different block structures while keeping its main skeleton. For example, changing the number of passes, and changing the operator on each pass. The last one is that a model architecture could gradually grow following some rules. For example, we can grow a model by adding layers to adapt the model to harder tasks. Similarly, we can gradually shrink a large model to adapt to easier tasks. All these model architecture modifications are very common during designing a new model. However, existing frameworks have a weak support to exploratory training because they only focus on a single DNN model. However, programming and training one DNN model is just one step of the exploratory training process. Although there are some tools for neural architecture search or hyperparameter optimization that drives exploratory training, but they usually lack modularity and programmability, make one NAS or HPU solution only applicable to one kind of neural architecture. On the other hand, the models explored during exploratory training could have high similarity among each other. These are great opportunities to leverage such similarity to speed up exploratory training process, which are missed by existing frameworks and tools. The way of programming DNN models has been evolved from programming with native C++, R language, MATLAB, to deep learning frameworks like PyTorch and TensorFlow. Given that we have understood the exploratory training process of designing deep learning models, we believe this is a good time to rethink DNN framework. What should we do to make the end-to-end experience of developing a DNN model much easier and faster? Here comes our system, Retiarii. Retiarii is designed as a deep learning framework for exploratory training rather than a single DNN model. It could make model exploration more systematic and programmable. Exploration strategies and algorithms become modular and fully reusable by various exploratory training tasks. Moreover, it enables cross-model optimizations to greatly speed up the exploratory training process. We position Retiarii as a go-to DNN framework to greatly help developers design new DNN models. Take the previous examples. We can see that exploratory training is a series of model mutations. The possible mutations build a model space. Exploratory training explores the models in this space to find out the best one. We design Mutator as a core abstraction. Mutator decouples model space from exploration strategy. Mutator could express arbitrary model space, making developers easily express a bunch of possible models they want to try. Exploration strategy can understand and search the model spaces that are expressed with mutators. Meanwhile, Mutator natively tracks the correlations between models, thus expose many cross-model optimization opportunities. Retiarii provides a new Mutator-based programming paradigm for users to program a model space rather than one single model. Due to the decouple of model space and exploration strategy, they are highly composable. A model space can try different exploration strategies. The cross-model optimization techniques in Retiarii greatly speed up the exploration process. Let's start with the Mutator-based programming paradigm. A model space is composed of base model and a sequence of mutators. Here is the 4-node sequential model. Let's say we want to replace the third node, max pool, with an inception cell. This inception cell could have 2 to 5 passes, and an operator on each pass can be chosen from convolution, depthwise convolution, and the max pool. For this model space, we write inception mutator. It takes a chain of 3 nodes and replaces the middle one with a newly constructed inception cell. It uses an API called choose to get the decisions from exploration strategies that decides how many passes to build and which operator is used on each pass. And finally, the mutator is applied to mutate the graph on the targeted part. During exploratory training, there are many decisions to make. For example, which models should be prioritized in search? How much time budget to give each generated model in training? Do we need to use early stop? Should weights be shared across models? These decisions could be made by exploration strategies or human. Currently, there have been a lot of good exploration strategies, such as reinforcement learning, grid search, evolution and annual algorithms, Bayesian-based optimizations, and a gradient-based search approach. More importantly, these exploration strategies are reusable by various user-defined model spaces. This is the architecture of Retiarii. JIT takes user-defined model space, including base model and mutators, then instantiates models following the model space. When instantiating models, mutators will be applied by interacting with Exploration Engine to get the decisions on which concrete model to instantiate. Exploration Engine exposes simple interfaces to allow users to customize their own exploration strategy. Humans can also interact with the exploratory training through this interface. The generated raw data flow graphs are optimized using cross-model optimizations before training. The training results are collected as a feedback to the exploration strategy for making better decisions. This table shows 8 out of 27 NAS solutions currently supported by Retiarii. Many model spaces can be constructed with 3 simple mutators: input mutator, operator mutator, and inserting mutator. Different model spaces and exploration strategies can be freely combined. Next, my colleague Zhenhua will introduce more details about Retiarii's cross-model optimizations and experimental results.
Models from a model space are usually similar to each other. They usually use the same training data and the same data preprocessing logic. Because they may be mutated from the same base model, they share some common layers. Moreover, some models may share weights with each other in order to leverage other models' higher accuracy and training progress. Based on these observations, we propose 3 cross-model optimization techniques in Retiarii to accelerate the exploratory training process. First, the dataset, preprocessing, and embedding of multiple models might be the same. Executing multiple models on the same server may lead to significant contention on CPU, especially for mobile models. When all these models use the same non-trainable prefix operations, the optimization of common sub-expression elimination will deduplicate them by merging them so that they are only executed once on CPU. Our micro-benchmark shows IMNAS-9 0.5 has a CPU utilization of 75%, even when running one model. Running more models in the server will lead to bottleneck on the CPU side. Using Retiarii CSE, the data loading and preprocessing will be deduplicated so that more models do not increase the CPU burden. Our micro-benchmark experiment shows Retiarii CSE can bring 3.4 times improvement on the training throughput for IMNAS-9 0.5 with a batch size of 224. Can also optimize the duplication of GPU-based operations. This example shows 4 models that use the same input and preprocessing on CPU and the BERT embedding on the GPU side. BERT is a very large model that occupies the most GPU memory consumption and the time of forward phase. In the CSE optimized model, we dedicate 1 GPU for BERT so that we can spare more GPU memory on other GPUs to pack more models. Also, the pipeline can be further improved by overlapping the forward of multiple models with the BERT of the next iteration. Our micro-benchmark of TextNAS on SST dataset with 4 V100 GPUs shows 1.97 times improvement on the total throughput. The layers in the middle of a model can also be deduplicated using operator batching, but due to limited time, I have to skip this part. Please refer to our paper for details. In the first end-to-end experiment, we evaluate how much Retiarii can accelerate neural architecture search. We choose 3 famous NAS solutions to evaluate: IMNAS-9, NAS-9, and MOBA-9. We chose the 3 because they cover different combinations of search spaces and exploration strategies. Both IMNAS-9 and NAS-9 use reinforcement learning to explore the search space, and NAS-9 and MOBA-9 use the same search space proposed by NAS-9. Because the large search space of the 3 NAS solutions, the exploration process could be very time-consuming. We compare Retiarii with 2 baselines. The exclusive execution strategy trains 1 model per GPU at a time. This is the most widely used strategy in NAS papers. We also try to enable NVIDIA CUDA MPS in the packing strategy to train multiple models per GPU at the same time. We compare the completion time of exploring 1,000 models on 4 V100 GPUs, such that each model will be trained for 1 epoch on ImageNet. Retiarii achieves up to 2.57 times speedup on the search time, mainly due to the optimization of packing multiple models per GPU and the common sub-expression elimination. When the batch size is 32, Retiarii can simultaneously run up to 22 IMNAS-9 models on 4 GPUs, because its models are much smaller than the other 2. This result shows an insight that small models can benefit more from Retiarii's current cross-model optimizations. In the baselines, we noticed simply packing multiple models in one GPU without cross-model optimization could even perform worse than the exclusive execution because of the heavy resource contention on the CPU. The second end-to-end experiment is to speed up weight shared training, which is a very common technique adopted in neural architecture search. Instead of training every instantiated model from the search space independently, weight shared training proposes to inherit weights of unchanged layers from previous models to avoid training every model from scratch. For example, here we have a model of 4 layers where only the second layer is mutable. The 3 candidates, ReLU, identity, and liquid ReLU together define the search space. In the first trial, ReLU is chosen to instantiate the model. The model is trained for a few mini-batches so that the weights of convolution and dense layer are updated. Then, the second trial is instantiated by choosing identity at the second layer. But the other 3 layers remain the same. Weight shared training will reuse the weights from the first trial to continue the training. After a few iterations, the third trial is instantiated by choosing liquid ReLU. Similarly, the weights are shared from the second trial before the training. In this way, the training of unchanged part will not be wasted in the new trials, which can greatly reduce the exploration time. Sharing weights using checkpointing could incur significant overhead. Many NAS solutions will manually build a supergraph using dynamic control flow to encode all possible choices in one graph. Each iteration will activate a path of the supergraph for training. In this way, we don't need to checkpoint and reload the weights for each instantiated model, which could save a lot of time from checkpointing and model initialization. Our macro benchmark shows over 6 times speedup using Retiarii's supergraph over checkpointing. Different from existing NAS solutions that manually build the supergraph, Retiarii can automatically build it directly using the mutator information. However, the supergraph will limit the search space size because it must fit into the GPU memory of a single GPU. It is also hard to scale a supergraph training to the large GPU cluster because it does not allow training a lot of trials at the same time. To break the limitations and speed up weight shared training, we propose mixed parallelism in Retiarii's cross-model optimization. To break the size limitation, we use model parallelism to partition the supergraph to multiple GPUs. Inside each partition, it still activates one path at a time. To mimic the weight shared training, we fit each partition with a different batch of data in a data parallel manner. Different partitions may share the common operations, which will be shared using parameter servers or collective communication primitives like our reduce. We evaluate a famous weight shared NAS solution called SPUS. Retiarii can reduce the training time from 46 hours to 7.45 hours, which is an improvement of 8.58 times. Meanwhile, Retiarii can achieve almost the same validation accuracy with the SyncBN-enabled data parallel training.
To conclude, Retiarii is a new DNN framework designed for exploratory training. In order to address more and more requirements on DNN model design, Retiarii provides a new interface for DNN model developers to design new models efficiently. They can easily express the models they want to try and leverage powerful exploration strategies to speed up the exploration. The simple but powerful mutator abstraction enables high expressiveness, reusability of exploration strategies, and plenty of rooms for system optimizations. Retiarii is our answer to the next generation of DNN framework for exploratory training. Its implementation for artifact evaluation has been open sourced on NI. We welcome any comments and suggestions. Thanks.